Thermoregulation at high temperatures. Background. In hot environments, mammals depend on behavior to minimize their thermal load, escape to shaded or cooler microclimates, use posture and orientation to wind and sun, restrict activity, become nocturnal, etc., and on evaporative water loss to rid themselves of excess heat. With regard to evaporative heat loss, Calder and King, 1974, page 326, arbitrarily subdivided the response to various air temperatures as follows. 1. Cool temperatures at which water loss should be minimized, both to reduce heat loss and as an adaptation to terrestriality. 2. An intermediate temperature range wherein evaporation is gradually increased as dry heat losses are proportionally reduced with smaller thermal gradients. And 3. Warm to hot temperatures at which evaporation must be actively increased to dispose of metabolic and exogenous heat loads. Some mammals are able to thermoregulate very well at high ambient temperatures via panting or sweating, whereas others have a very limited capacity. Hence, there is no general approach to calculating evaporative water loss under these conditions. Campbell, 1977, page 85. However, the ratio of evaporative heat loss to metabolic heat produced can be used to quantify a species' capacity for evaporative cooling and to make comparisons between species. Comparison of procyanid responses to heat stress. Potus flavus. This species lives in neotropical forests of Central and South America. It is nocturnal, arboreal in habit, and appears to be the most heat-sensitive of these procyonids. Its upper critical temperature is at 30 degrees Celsius to 33 degrees Celsius. Table 7, Mueller and Coulter, 1977, Mueller and Roast, 1983. It begins to pant at about 30 degrees Celsius, but its efforts at evaporative cooling are very ineffective. At 33 degrees Celsius, Potus flavus can dissipate 33% of its metabolic heat via evaporative water loss, but at 35 degrees Celsius, the efficiency of this mechanism falls to 20%. Mueller and Roast, 1983. Consequently, when exposed to air temperatures above 33 degrees Celsius, any kind of excitement causes its body temperature to rise rapidly in an uncontrolled manner. Mueller and Coulter, 1977, Mueller and Roast, 1983. These animals rely on their nocturnal and arboreal habits to keep them out of situations that could lead to hyperthermia. Mueller and Coulter, 1977, Mueller and Roast, 1983. Nasua and Nasua narica. Nasua is abundant in tropical and subtropical South America, whereas Nasua narica occupies the same climates in North America from southern Arizona and New Mexico, south through Panama, and on into Colombia and Ecuador. Hall and Kelson, 1959, page 892. Ewer, 1973, page 391, page 392. Poglayan Newell, 1975. Both coatis are diurnal and forage primarily on the ground. Kaufman, 1962, pages 185 through 188, 1987. Poglayan Newell, 1975. Noack and Paradiso, 1983, page 982. Consequently, they are exposed to a more severe thermal environment while active, higher air temperatures and solar radiation, than are nocturnal procyonids. Both coatis are more heat-tolerant than Potus flavus. Their upper critical temperatures are higher, 33 degrees Celsius to 35 degrees Celsius, Table 7. They can tolerate air temperatures of 35 degrees Celsius without raising their body temperatures. Cheviat Hugo et al., 1980. Mugas et al. In preparation. and they have a greater capacity for evaporative cooling than Potos flavus, Mugas et al. In preparation. The greater heat tolerance of these coatis is compatible with their diurnal habits and widespread distribution in a variety of forest habitats in both tropical and subtropical areas of the Western Hemisphere. Bassiriscus astutus. In addition to living in neotropical forests of Mexico, Bassiriscus astutus also flourishes in hot, arid climates, and it has extended its range much farther north than Nassau anarica. Hall and Kelson, 1959, pages 881-892. Pogley and Newell, 1975. Kaufman, 1982. Its upper critical temperature is higher, 35.5 degrees Celsius, Table 7, than that of Potos flavus, but it is comparable to those of Nassau and Nassau anarica. Its capacity for evaporative cooling is well developed. At 40 degrees Celsius, Bassiriscus astutus is able to dissipate 100% of its resting metabolic heat via evaporative water loss, and at 45 degrees Celsius, it is able to dissipate 172%. Chevalier, 1985. In spite of its great capacity for evaporative cooling, this species is nocturnal, a habit that, along with its low basal metabolic rate, should allow it to keep thermoregulatory water requirements to a minimum. Procyon lotor. Our data suggested that upper critical temperature for Procyon lotor in winter was comparable to that for Bassiriscus astutus, 35 degrees Celsius, and that in summer it was even higher. When exposed to temperatures near the upper end of its thermoneutral zone, Procyon lotor increased the gradient for passive heat loss with a controlled rise in body temperature, Figure 6. In summer, its capacity for passive heat loss was enhanced by the molt of its heavy winter fur. Procyon lotor's capacity for evaporative cooling also appeared to be well developed, although our animals were not heated to the point that evaporative cooling was fully expressed. Figures 4 and 5. However, Procyon lotor is nocturnal, and this may allow it to eliminate or at least reduce the need for evaporative cooling, even in hot climates. Thus, Procyon lotor appears to be well equipped physiologically and behaviorally to cope with thermal demands of hot environments in its distribution. Procyon cancrevorus. Unfortunately, data for the crab-eating raccoon are not complete enough at high temperatures to include it in this survey. Summary. This comparison demonstrates that capacity for evaporative cooling, tolerance of an elevated body temperature to enhance passive heat loss, and behavioral avoidance of thermal stress are the primary methods used by proconids to thermoregulate at high temperatures. Procyon lotor and Bassiriscus astutus, whose distributions extend into temperate regions, have developed these abilities to a greater extent than other proconids. Potos flavus, whose distribution is confined to lowland tropical forests, has the least ability in this regard. Nassau and Nassau anarica appear to have thermoregulatory abilities that are intermediate to those of Bassiriscus astutus and Potos flavus. This suggests that ancestral proconids may have had poor to modest ability to thermoregulate at high temperatures, a condition that would have limited their ability to leave the thermal stability afforded by tropical forests. Dispersal into temperate climates, therefore, required not only increased cold tolerance, but also selective enhancement of those mechanisms used in thermoregulation at high temperatures. Table 11. Distribution by climate of selected proconid species. I am not reading the table. Composite scores of adaptive units and geographic distribution. In Table 11, procinid species are arranged in descending order with respect to the number of major climates that are included in their geographic distributions. Hall and Kelson, 1959, pages 878 to 897. Pogley and Newell, 1975. Courtlock and Ramirez Pulido, 1982. Nowak and Paradiso, 1983, pages 977 through 985. Composite scores ranged from a high of 1.47 for Procyon Lotor to a low of 0.39 for Potos flavus, whereas Naswa narica, Procyon cancrivorus, and Basiliscus astutus had intermediate values ranging from 0.64 to 0.79, Table 12. Figure 8 demonstrates that there is a direct relationship between the number of climates these species occupy and their composite scores. Regression analysis, y equals 2.68 times x plus 0.24, where y is number of climates and x is composite score, demonstrates a high degree of correlation between these variables, r equals 0.94. and indicates that 89% of the variance in distribution can be explained by composite scores. The various combinations of adaptations expressed by these species do, therefore, play a role in delimiting their climatic latitudinal distributions. Procyon Lotor's normalized scores were higher in all categories than those of other procinids. Procyon Lotor, therefore, possesses those traits that have allowed it to become the premier climate generalist of the procinid family. As an adaptive unit, these traits provide Procyon Lotor with the physiological and behavioral flexibility required to take full advantage of a wide range of climates and habitats, and its distribution verifies that it has done so. Even so, it is probably not fair to assume that this species represents a perfect physiological match with climate over its entire distribution. Procyon Lotor is, in many respects, still a forest-dwelling species, and its ability to expand its distribution into other habitats, such as prairie and desert, may well be due, in part, to its use of behavior to take advantage of favorable microclimates in otherwise hostile environments. Bartholomew, 1958-1987. This feature of Procyon Lotor's biology needs to be further examined. Table 12. Normalized and composite scores for selected procinids. HBR equals ratio of measured to predicted basal metabolism. Table 7. CMWR equals ratio of measured to predicted minimum thermal conductance. Table 7. DDR equals ratio of food categories actually utilized by each species to total food categories eaten by all 6 species, calculated from Table 9. R max R equals ratio of calculated to expected R max, Table 10. I am again not reading the table. All 5 species with low basal metabolic rates have composite scores less than 1. Table 12, Figure 8. 4 of these 5, Naswa narica, Procyon cancrivorus, and Potos flavus, have basal metabolisms to ratio of measured to predicted values ratios that are 0.6 or less, which indicates they are the least cold-tolerant procyonids. McNabb, 1966. These 4 species also are confined to either tropic or tropic and subtropic climates. Table 11. This suggests that these species share a common thermoregulatory adaptation that represents a specialization to these climates. Attendant with this adaptation, however, is a high cost of thermoregulation at temperatures below their lower critical temperature. And this must be an important factor in limiting their distributions to tropic and subtropic climates. Differences in their distributions within these climates, therefore, must hinge more on differences in their DDR. Ratio of food categories actually utilized by each species to total food categories eaten by all 6 species. And ratio of calculated to expected intrinsic rate of natural increase. Values. Then on differences in their basal metabolism to ratio of measured to predicted values ratios. This is supported by the fact that Potos flavus, which has the lowest ratio of food categories actually utilized by each species to total food categories eaten by all 6 species, DDR, and R max R values is confined to a single climate, whereas Naswa Narica, and Procyon Carnivorous each possess larger DDR and R max R values and are found in 2 climates. Thus, Potos flavus, with its highly specialized diet and low reproductive potential, is the most ecologically specialized of these prosonids, and its distribution is limited to the single climate that can provide its requirements. Naswa Narica, and Procyon Carnivorous are less specialized and thus show more ecological flexibility in their distributions. Figure 8. Relationship between number of climates in which a species is found and its composite score. Symbols for Naswa overlap at coordinates 0.64, 2. Solid line represents linear regression of climates y on composite scores x. Y equals 2.68 times x plus 0.24. R equals 0.94. Basiliscus astutus, the other species with low basal metabolic rate, is found in 3 climates, which indicates that it has greater ecological flexibility than Naswa Narica, or Procyon Carnivorous. DDR and R max R are comparable for these 4 species, Table 12. This suggests that the greater ecological flexibility of Basiliscus astutus is derived largely from its greater cold tolerance. Basiliscus astutus has a more insulative pelt than these other prosonids. Ratio of measured to predicted values equals 0.85, Table 7. So its basal metabolism to ratio of measured to predicted values ratio is higher, 0.80, Table 12. This and its greater capacity for evaporative cooling, Chevalier, 1985, allows Basiliscus astutus to take advantage of a wider range of thermal environments than these other species. However, even with its higher HBr to CMWR ratio, the composite score for Basiliscus astutus is not much different than those for Naswa Narica, and Procyon Carnivorous, Table 12. Consequently, Basiliscus astutus is found in more climates than would be predicted for it on the basis of its composite score, Figure 8. This suggests that either the HBr to CMWR ratio carries greater weight in determining distribution than is reflected in this analysis, or as has been described for some other species, Bartholomew, 1958-1987, Basiliscus astutus may extend its distribution farther than expected via use of its behavior. In either case, for prosonids with low basal metabolic rate, Basiliscus astutus represents the pinnacle of adaptation for climate generalization. Evolution of metabolic adaptations. Evolution of low basal metabolic rate. A radiation of frugivorous and omnivorous Procyon, Table 1, occurred in the Middle and Late Miocene of North America. It included origins of such terrestrial genera as Cyanasua, Naswa, and Procyon, Webb, 1985b. The earliest prosonid genus to find its way to South America was Cyanonasua. an omnivorous carnivore that presumably split, along with its sister genus Arctonasua, from a common North American ancestor. Baskin, 1982. Webb, 1985b. Cynonassua, about the size of present-day raccoons, was adapted to a wide range of habitats and was probably comparable to modern raccoons with respect to the breadth of its feeding habits. Webb, 1985b. Marshall, 1988. Because North American Arctonasua was about the same size as Cynonassua, Webb, 1985b, and shared a number of characters with it, Baskin, 1982, we speculate that it also may have had similar habits and occupied similar climates and habitats. Basariscus, another member of Procyon, had an even earlier origin in tropical North America, Webb, 1985b. The origin of the small arboreal forms Potus and Basarisson, subfamily Potacinae, is obscure, but is thought to have occurred in the rainforests of Central America, Webb, 1985b. What were the metabolic capabilities of these early proconids? We do not know, but for several million years, from middle to late Miocene, proconids lived in tropical and subtropical forests of Central and North America. Webb, 1985b, Marshall, 1988. Then in the Pleistocene, several modern forms crossed the Panamanian land bridge into similar habitats and climates in South America, but none of them appear to have spread far enough northward to have crossed the Bering Land Bridge. Several million years exposure to a tropical environment, with its continuous high temperatures and modest range of thermal extremes, would have favored selection of metabolic and thermoregulatory traits that would minimize energy requirements. A lower than predicted basal metabolic rate, a prolonged or continuous molt resulting in very little annual change in minimum thermal conductance, and a modest capacity for evaporative cooling. In addition, we would expect selection to have favored a diverse diet, good reproductive potential, and behavioral flexibility to utilize a variety of habitats within these climates. Our analysis has shown that such characteristics are the norm for extant members of this family living in tropical and subtropical climates, and we speculate that these traits also were common to early proconids and served to restrict them to these climates. Our speculation is supported by the fact that their known fossil history from the Miocene is confined to geographic areas that had tropical and subtropical climates. Later on, during Pleistocene glaciations, tropical and subtropical forests shrank, savannas expanded, and temperate climate was pushed toward equatorial regions. The opposite occurred during interglacial periods. Raven and Axelrod, 1975, Webb, 1977, 1978, Marshall, 1988. Consequently, mid-latitudes experienced alternating periods of temperate and tropical, or at least subtropical, climate change. Selection of characteristics that would have adapted a species with low basal metabolic rate to temperate as well as tropic or subtropic climates would have occurred in mid-latitudes at the temperate edge of these tropical advances and retreats. Our analysis indicates that, for this purpose, selection would have favored lower than predicted thermal conductance, seasonal molt, increased capacity for evaporative cooling, increased tolerance of elevated body temperature, increased flexibility of thermoregulatory behavior, food habits that provided for year-round access to a high-quality diet in all three climates, and a higher than predicted intrinsic rate of natural increase. Basariscus astutus is the only species with low basal metabolic rate that has all these characteristics, and it is the only one of them that has added temperate climate to its distribution, Table 11. This suggests that Basariscus astutus is a species that evolved away from the norm for proconids with low basal metabolic rate, toward characteristics that allowed it to become more of a climate generalist. Potos flavus, with its dietary specialization, Low tolerance to high temperatures and arboreal mode of existence has become a highly specialized species, totally dependent on tropical forests for its survival. As such, it also represents a species that has evolved away from the procinid norm and portrays the extreme in climate specialization. Olingus Bassarison gabi, Table 1, may be similar to Potos flavus in this respect. See also Table 10. This suggests that of the extant procinids, Nasua nasua, Nasua narica, and Procyon cancrivorus have retained metabolic and behavioral characteristics that are closest to those of their Miocene ancestors. Evolution of high basal metabolic rate. Between the time that Cynonassua appeared and the Panamanian land bridge was established in the Upper Pliocene 4 to 5 million years ago, northern climates continued their gradual cooling. This, along with ongoing elevation of the continents and continuous modification of their mountain ranges, served to shrink the tropical forest and create pockets of climactic instability within it and on its edges. Darlington, 1963, pages 578 through 596. Marshall, 1988. In areas of instability, selection would have favored traits that provided for a broader range of thermal tolerance. Higher basal metabolic rate, improved insulative quality of pelt, a more sharply defined molt cycle, improved capacity for evaporative cooling, greater diversity of diet, and higher intrinsic rate of natural increase. Consequently, by the Upper Pliocene, two metabolically distinct groups of procinids could have been established. Those species with low basal metabolic rates living in climatically stable forests, and those with higher basal metabolic rate living in unstable tropical, subtropical, and perhaps temperate climates. Procyon lotor is the only extant procinid with a high basal metabolic rate. Procyon cancrivorus is its congeneric counterpart in Central and South America, Table 1, and the two species are sympatric in Panama and Costa Rica. However, in terms of its metabolism, thermal conductance, molt, diversity of diet, intrinsic rate of natural increase, and climactic distribution, Procyon cancrivorus shares more in common with other procinids than it does with Procyon lotor. Tables 7, 11, and 12. Figure 8. This suggests that metabolically, Procyon lotor portrays a divergent line of this genus that arose as the result of a series of mutations that gave rise to different metabolic characteristics. This view is in keeping with a recent phylogenetic analysis of this family that shows the genus Procyon to be highly derived. Decker and Wozencraft, 1991. Consequently, it would be instructive and would add to our knowledge of the evolution of climactic adaptation to know more about the genetic relatedness of these two species as well as their historical relationship. Genus Procyon appears in the fossil record. Hemphillian and Blancan ages. Baskin, 1982. Prior to Pleistocene glaciations. During the Pleistocene, there were 4 different glacial advances and retreats in a relatively short time period, the first appearing little more than 1 million years ago. Darlington, 1963, pages 578 through 596. Webb, 1985a. Marshall, 1988. Glacial retreats created pulses of time during which subtropic and temperate climates advanced toward the poles into areas with large seasonal differences in light-dark cycles, whereas glacial advances pushed these climates southward into areas having smaller seasonal differences in light-dark cycles. Raven and Axelrod, 1975. Webb, 1977, 1978. Marshall, 1988. Those members of the genus Procyon caught in these wide latitudinal fluctuations would have experienced conditions favorable to continued selection for characteristics conducive to physiologic adaptation to a wide range of climatic conditions. Procyon Lotor is the only member of its genus to have survived the selective process, and as we have seen, it does possess traits that adapt it to a wide range of climatic conditions. Primary among these is its higher basal metabolic rate, which provides it with advantages not shared with other proconids. See earlier discussion. 3 other adaptations also have had a profound influence on Procyon Lotor's ability to generalize its use of climate. 1. The increased insulative quality of its pelt, coupled with its sharply defined molt cycle, which allows for a large annual change in thermal conductance. 2. Its annual cycle of fat storage. And 3. A diverse, high-quality diet. The first 2 of these adaptations required evolution of neuroendocrine pathways capable of responding to time-dependent environmental cues such as changing day length, changing temperature, etc. Such conditions would have been available as selective stimuli in high-latitude forests and savannas of interglacial periods. Procyon Lotor's elevated basal metabolic rate would have increased its overall energy requirement, and it makes good intuitive sense, therefore, that evolution during the Pleistocene also would have favored selection of a diverse diet containing many items of high nutritive value. Summary. Our analysis has illustrated that within Proconidae, there are 2 distinct modes of metabolic adaptation to climate. One is typified by those species with low basal metabolic rates, Bassaricus astutus, Nasua nasua, Nasua narica, Procyon cancrevorus, and Potos flavus, and the other by Procyon Lotor with its higher basal metabolic rate. Those with low basal metabolic rates have more restricted geographic distributions, and with the exception of Bassaricus astutus, they are all confined to tropical and subtropical areas. The fossil history of this family indicates that it had its origins in tropical forests of North and Central America. This indicates that those proconids whose distributions are still primarily restricted to tropical forests share many of the metabolic adaptations characteristic of their ancestors. We speculate, therefore, that ancestral proconids had a lower than predicted basal metabolic rate, a pelt with modest to poor insulative quality, good thermogenic ability but poor heat tolerance, modest to poor capacity for evaporative cooling, no well-defined molt cycle, no cyclic period of fattening, nocturnal habits, and a modestly diverse diet of high enough quality to provide for an average reproductive potential. Although this pedigree contributed to the success of this family in tropical and subtropical forests, it limited the ability of its members to expand their distributions into cooler, less stable climates. Viewed in this perspective, Procyon Lotor's high basal metabolic rate, extraordinarily diverse diet, well-defined cyclic changes in fat content and thermal conductance, high level of heat tolerance, high capacity for evaporative cooling, and high reproductive potential all stand out in sharp contrast to the condition described for other proconids. This suggests that the North American raccoon represents culmination of a divergent evolutionary event that has given this species the ability to break out of the old proconid mold and carry the family into new habitats and climates. Appendix. List of symbols. A. Potential age of females first producing young. B. Potential annual birth rate of female young. Ca. Conductance of air. Cd. Conductance of dead walls. Cm. Minimum thermal conductance. Cmd. Minimum dry thermal conductance. Cmw. Minimum wet thermal conductance. Cmwr. Ratio of measured to predicted minimum wet thermal conductance. Ct. Total conductance. Dd. Diversity of diet. Ratio of food categories actually used by a species. DDR. Ratio of food categories actually used by a species to the total number of food categories taken by all species tested. E. Evaporative water loss. EC. Ratio of evaporative heat lost to metabolic heat produced. EEQ, oxygen equivalent for heat lost by evaporation. HB, basal metabolic rate. HR, lowest resting metabolic rate at each temperature. HBr, ratio of measured to predicted basal metabolic rate. M, mass of animal. MW, mass of water. N, potential age of females producing their final young. Rmax, intrinsic rate of natural increase. Rmax E, expected intrinsic rate of natural increase. Rmax R, ratio of calculated to expected intrinsic rate of natural increase. RQ, respiratory quotient. TA, chamber air temperature. TB, body temperature. TLC, lower critical temperature. TN, thermoneutral zone. TUC, upper critical temperature. T, time. .VA, rate of airflow through U-tubes. .VE, rate of airflow into metabolism chamber. Alpha, active phase of the daily cycle. Greek Y-looking thing. Heat equivalent of oxygen. Greek triangle thing, but not delta. Heat of vaporization of water. Greek P-looking thing. Rest phase of the daily cycle.